Now let's take a look at the running time of Kruskal's algorithm, and then we'll look at the proof of correctness of Kruskal's algorithm. How long does it take to sort the edges by increasing weight? This takes order m log n time. M is the number of edges and n is the number of vertices. Note, of course, m log n is the same as m log m. Now, how long does it take to do this step? How long does it take to check whether adding edge e into x creates a cycle or not? What exactly do we want to check to see whether it creates a cycle or not? Look at the subgraph on this set of edges x. Now in this subgraph, let C of V be the component containing V, and C of W is the component containing W. Now to see whether the edge E creates a cycle when we add it into this subgraph, we want to check whether there's already a path between V and W. If there already is a path between V and W, then the components containing V and W are the same. V and W are in the same component. So what this step does is it checks whether the component containing V and the component containing W are different. So if V and W are in different components, then we add the edge E into X. Now how do we check the component containing V and the component containing W? Well, we use this data structure, this simple data structure known as union find data structure. Using this data structure, it takes order log n time per operation. So it takes order log n time to check the component containing V and the component containing W, and then we can see whether they're the same or different components. And then once we add this edge E into X, then we can update the component containing V and the component containing W. We can merge those two components in order log n time. So the union find data structure takes order log n time for each check operation in order to check whether the component containing V and the component containing W are the same or not. And it takes order log n time to do a merge operation where we merge the component containing V and the component containing W because we added edge E into X. Now I'm going to skip the details of the union find data structure since many of you may have seen it in a data structures class before. And if you haven't seen it before, then you can review it in the textbook. But it's a very simple data structure using this notion of rooted directed trees. And once we have this data structure which has order log n time per operation, then the key fact is that we're doing at most m operations. And then since there are order m operations, each one taking order log n time, then the total run time for this step 3 is order m log n again. So step 1 and step 3 both take order m log n time. So the total runtime is order m log n for the whole algorithm. Now what I want to focus on in this lecture is not the data structure, but the proof of correctness of this algorithm. Why does the greedy approach work for this problem?